In 60 days, a space telescope is launching from Kennedy Space Center that will photograph 1 billion galaxies in a single mission. For 30 years, Hubble has been humanity's eye on the deep universe. Its achievements are legendary, but it has only scratched the surface. And the telescope arriving in August will reveal how little we have actually seen. It is called the Roman Space Telescope, and it represents a fundamental shift in how astronomy works. Hubble operates like a telescope in an old observatory. You point it at a target and stare. Roman operates like a survey instrument. It looks wide. It looks fast. It prioritizes coverage over focus, and in doing so, it changes what questions we can answer about the cosmos. Inside Roman is a camera called the Wide Field Instrument. It does something no other space telescope has achieved. It combines an impossibly wide field of view with extreme infrared sensitivity. The camera contains 18 separate detectors, each one built to measure light in the infrared band. Each detector holds 16 million pixels. Together, those 18 detectors contain more than 300 million pixels. A modern smartphone camera is roughly 12 to 16 megapixels. Roman's camera is 20 times larger, and it sees colors invisible to the human eye, wavelengths where many of the universe's most distant and oldest objects shine brightest. This is not just a bigger sensor. The way these detectors are assembled changes everything. When you combine them, you do not simply get more pixels, you get something qualitatively different. You get a field of view that spans 1/4 of a square degree of sky. That does not sound large, but in astronomy, it is vast. To understand why, compare it to Hubble. Hubble's infrared camera, the WFC3IR, observes about the same area of sky as a postage stamp held at arm's length. Roman's field of view is 100 times wider. In a single exposure, Roman captures what would take Hubble roughly 100 separate pointings to assemble. And because Roman maintains the same spatial resolution as Hubble, measuring objects at scales of 0.11 arcseconds, that detail is preserved. You are not trading sharpness for width. You are getting both. Hubble was revolutionary. It detected galaxies formed just a few 100 million years after the Big Bang. It measured the accelerating expansion of the universe, a discovery that won the Nobel Prize in physics. It found supermassive black holes at the centers of galaxies. It characterized the atmospheres of planets orbiting other stars. And it did all of this while being constrained by the limits of its field of view. Every time Hubble wanted to study a new region of sky, it had to point there and wait. Roman removes that bottleneck entirely. The speed advantage is transformative. Hubble can survey the sky, but it does so slowly. To map the same area that Roman photographs in one shot, Hubble would require months of continuous observation, assuming the telescope had no other tasks. Roman will accomplish the same work in hours. Science projects that would consume years of Hubble time become possible within weeks of Roman's operation. The shift is not just quantitative, it is a change in the kind of science that becomes feasible. But raw speed and wide vision are only the foundation. Roman is targeting 3 specific mysteries that have haunted cosmology for decades. The first is dark energy. Astronomers know it exists because observations clearly show that the universe's expansion is accelerating. Galaxies are being pushed apart faster and faster, and they are moving away from us more rapidly than they were billions of years ago. But what causes this acceleration? Physicists have no idea. Dark energy comprises 95% of the universe by mass energy equivalent, and we understand almost nothing about it. Dark energy is the largest mystery in physics, and it has resisted every attempt at explanation. Roman will measure the light coming from billions of galaxies across billions of years of cosmic time. By studying how the universe expanded at different epochs, Roman can create a precise map of dark energy's strength over time. If dark energy is constant, Einstein's cosmological constant hypothesis is correct, and we need to explain why it has the value it does. If dark energy changes, we need entirely new physics. The stakes of that measurement are hard to overstate. The second mystery is dark matter. We can see dark matter's effects everywhere. Its gravity shapes the rotation of galaxies, making them spin too fast to hold together unless there is far more mass than we can see. It bends light from distant objects, a phenomenon called gravitational lensing. It bridges the gaps in every computer model we build to understand how the universe works. But we have never directly observed dark matter. We do not know what it is. Roman will use a technique called gravitational microlensing to search for it. When a star or a massive planet passes in front of a distant galaxy, the gravity of that foreground object bends the background galaxy's light, magnifying it. The magnification is small, but measurable. Roman will watch for these events continuously, tracking when the light curves change. Each microlensing event reveals the presence of an object we cannot see directly. Over a full mission, those events will add up to thousands of discoveries, mapping dark matter's distribution and potentially identifying an entirely new class of objects. And those microlensing events also reveal exoplanets. When a foreground star's gravity bends and magnifies the light from a background galaxy, any planets orbiting that foreground star will add their own subtle signature to the light curve. Roman's precision is such that it can detect planets as small as Earth-orbiting distant stars. The mission will discover more than 1,000 new exoplanets, perhaps far more. For many of these worlds, Roman can characterize their atmospheres using a specialized instrument called a coronagraph. This device blocks out the glare of a star, allowing Roman to image the planet directly and analyze the light reflecting off it. That light carries chemical fingerprints. The presence of oxygen, methane, and other gases might indicate life. For the first time, Roman will make it possible to search for biosignatures in the atmospheres of worlds far beyond our solar system on a systematic basis. The spacecraft itself is built to last. It weighs 8,000 kilograms and is being packaged aboard a SpaceX Falcon Heavy rocket. After launch, it will coast for roughly 1 month to the Sun-Earth L2 Lagrange point, a gravitational sweet spot about 1.5 million kilometers from Earth, roughly 4 times the distance to the Moon. There, Earth, Sun, and spacecraft remain in gravitational balance, so Roman does not waste fuel fighting gravity. It simply floats, collecting photons from the early universe. NASA plans for the mission to last between 5 and 10 years, though the telescope may operate longer if its instruments remain healthy. During that time, Roman will measure the light from approximately 1 billion galaxies. Every galaxy carries information about what the universe looked like when that light began its journey, sometimes billions of years ago. Stacked together, those observations will answer questions that have defined astronomy for a generation, and they will certainly raise new ones that we cannot yet imagine. In 2 months, we find out what they are.